Welcome. In this video I'm going to talk about how to do statistical significance tests for differences between two groups or two conditions in an experiment. For that I'm going to very briefly review what statistical significance testing is all about. Then I'm going to introduce a difference in the way you could design an experiment that influences the kind of test that we can run. And lastly, I'm going to show how to actually run t-tests, the most common test used when there are two conditions or two groups, so how to run such t-tests in R. So statistical significance testing is basically something that we need to do whenever we have a sample and we observe a difference in that sample. So it might be a difference between two groups, it might be a difference between men and women performing differently on some task, or it might be a difference between two experimental conditions, for example, drunk and sober, where again there might be a difference in some performance measure. But if we observe something like that in a sample, we will need to ask, how likely is it that this expresses something about the population that the sample is drawn from? Is it likely that my observation is just due to chance? Or am I warranted to believe that there's a real difference in the population? Basically, the whole point of significance testing is to quantify the probability that I would have observed that difference if only chance had been at play. And that helps me to decide what I should believe after my experiment. So there's one important consideration when it comes to designing experiments that also shapes how we test for significance. And that is the question whether we run an experiment between or within participants. The most classical idea that we have also discussed so far for an experiment is that I take my participants, split them into two groups. Each group experiences something different, and then I try to see whether there's a difference between those two groups. In the example here, one of the groups might be listening to music while they're studying for a test. The other group studies in silence, and they test whether there's a difference. That is called a between participant design. The alternative would be to get all the participants together and then get all the participants to once study while music is playing and then to study in silence, a so-called in-participant design. How would we choose between them in planning a study? There are some advantages and disadvantages to each of them. So firstly, the in-participant design is very attractive because it makes sure that there's no difference between the groups because the groups are the same. So because of that, we need fewer participants. But those participants will understand what the different conditions are since they get to experience all of them. So that limits the blinding, the experimental blinding we can do. It also introduces some issues around order effects. If all participants first study with music, then study in silence, they might just have improved their studying skills the first time around. So there are things like counterbalancing that you need to do in participant experiment, that different participants experience a different order of the conditions. And thirdly, each participant has to put more effort in. If the task is very simple, that's not a problem. If the experiment requires more commitment, it might just not be feasible to run it within participants. So between participant design then conversely only requires participants to do one thing. And that allows for complete blinding. They don't need to know what the other options are, they don't need to know what they are going to do when they go into the experiment. So there's more control in that regard. But obviously we'll need a much larger sample. It needs to be at least twice as large because each participant contributes only one rather than two data points. But because there are now more differences between the groups, it needs to be even more than twice as large. And then we still have a higher risk that random variations between the two groups distort our results. So when we can choose between those two options, that's a choice to be made deliberately. Of course, sometimes we can't. If we're interested in the impact of gender, that will always be a between participants variable. We can't decide to test the same participants once while they're male and once while they're female. So sometimes certain variables are between participants, often we have a choice in how we want to pursue the research. Depending on that choice, we're asking slightly different statistical questions, and it's important to be clear on which question we are asking. So in a between participants design, we calculate the mean of each of the groups, of men, of women, and then we test whether we can confidently conclude that those means are different from each other. In a within participants design, we do something different. We calculate the difference on the condition for each participant, and then we calculate the mean, the average, of those differences. The question becomes, is the average difference now different from zero, significantly different from zero? To answer each of these questions, we need to run slightly different tests. And usually we would run formal statistical tests on here. We could also do bootstrapping or simulations, as covered in an earlier video. But usually, since this is a very simple, well-established test, we would use a formal test. What are formal statistical tests? Well, there are many of them, but they're all based on a similar idea. They're based on the idea that we can calculate some test statistic, that we can then take the test statistic and compare it against a known null distribution, so against the distribution that it would follow if there was no difference, and then get a p-value from that. So we can then get the probability that our data would have been observed if there had been no difference in the population, and use that to decide what to believe. There are many different tests. Which one we are using depends on the distribution of our data, so is it normally distributed or not, and it depends on how many and which variables we have. T-tests, the only test that I'm going to focus on for the moment, compare the mean between two groups or between two conditions. And these groups or conditions are generally defined then by a categorical variable that has two levels. Then we need to distinguish between a paired t-test, where the idea is participants are paired, so that's what we would use in participant design, and an independent samples t-test, where basically I have two samples that I'm comparing. Both of these can be run in R using the t.test function, but there needs to be then additional information to tell R which one to run. So let's look at a study for which we actually need both types of tests. So let's imagine an experiment where we try to see to what extent a TV going on in the background distracts students from studying. TV running in the background is a very common thing in many homes, so it matters whether or not that's a big problem for students. So we put our participants into different conditions, TV on or off, get them to read the text and get them to answer comprehension questions. Now, because we want to have as much statistical power as possible, let's run that part as a within participant design. So each participant, one studies with the TV on, one studies with the TV off. But then we might have a different question about individual differences. Are extroverts less affected by this distraction than introverts? That we can't run within participants, we can't make our participants introverts and extroverts, so here we are comparing two different groups. Actually, the study and the data are based on this article from 1994. And in that study, in the descriptive statistic, they find support for both implicit hypotheses. So they found that when the TV was off, participants were able to to read better and then subsequently to answer more comprehension questions correctly. And when the TV was on, extroverts could cope with that better than introverts in their sample. Now, what does it tell us about the broader population that the sample was drawn from? That's exactly what we now need to run formal significance tests for. So firstly, to compare TV on and TV off, it's a case of an in-participant design, so we are running a paired t-test. For a paired t-test, we call the t-test command, we give it the two variables, and then say that those variables are paired. So what I was doing here is for each participant, it calculates the difference between the two variables, takes the average, and then estimates how likely we would have been to observe that average under the null hypothesis of there being no difference in the population. The first important piece of information we get here is that the p-value is 0.04. So it's about 4% likely that we would have observed such a difference between the two groups if there had been no difference in the population. That's quite unlikely, it's smaller than 5%. So we would typically say we have good reason to believe that there is a difference. The other good piece of information that R automatically gives us here is the confidence interval. So we can see what we are able to say about the strength of the effect. And that's actually not very much here. This confidence interval doesn't include 0, but it goes quite close to 0. So we can't say that there's a big effect. There might actually be only a tiny effect, but we can say, we can be quite confident that there is some effect. So for the in-participant part, does a playing TV distract from studying? We can say the study provides statistically significant evidence that that's the case. Now, the independent samples part, there the command looks a little bit different. This time we introduce a formula notation and say score TV is predicted by this personality type. The tilde symbol generally means is predicted by in statistical tests in R. And of course we drop the paired attribute as the paired argument because it's no longer paired. So this is now running an independent samples t-test. R confirms to us the averages. We've seen this before. There is an average. There's a difference in the averages between the two groups, but that difference is not statistically significant. Why is that? Our sample size here is really tiny. The whole study had 20 participants, so now we have 10 participants in each group. To detect a significant effect with such a small sample would need to be lucky and the effect would need to be huge. Clearly that's not the case here. So we can't conclude that TV has a different effect on extroverts and introverts. We might want to say, well, from the descriptive statistics it looks like that, so it's worth investigating it in the future. But if our data could have easily occurred due to chance, in fact, in more than 20% of the cases, it would have occurred if there was no difference in the population. This is also shown by the fact that the confidence interval now includes 0. So we can't say that the difference between the groups is different from 0. There's no statistically significant difference. So when can we use t-tests? So we can use t-tests when we want to see whether two groups or conditions differ on a variable that is continuous, because t-tests are about comparing means, and obviously the mean of a categorical variable would be meaningless. There can only be two groups. If we have more than two groups, we need to use a different test that we're going to explore in the future. And the continuous variable needs to be normally distributed in each of the groups. And this is not very sensitive. Clearly, a group of 10 participants, a set of 10 values, cannot form a perfect normal distribution, but it needs to be close enough. If it looks completely different on the histogram, we need to do something about that. We need to then either think about transforming the variable. We saw that in the gapminder data set, where we could use a logarithmic transformation to turn this shape into a straight line and make the variable thereby more normally distributed. Or we can use something that's called the Mann-Whitney U-test, which is similar to a t-test, but doesn't require normality. We'll not get there anytime soon in this course. Normality is very often given, so usually we can use the t-tests. There's one more assumption that t-tests and actually many statistical tests tend to make. They tend to assume that the variance, so the spread, is the same in each of the groups. And of course the variance is just the square of the standard deviation, so this is the same as saying the standard deviation is the same. Obviously it doesn't mean that they have to be exactly the same number in our sample. It means we should be able to believe that they are the same in the population. There are many ways of testing that. There are formal tests such as Levine's test. More relevant for us are some rule of thumbs. So what we would generally do is we would try to see is the largest standard deviation divided by the smallest standard deviation, is the difference there less than 2. In a t-test we obviously only have 2 groups, so one standard deviation divided by the other. Do we get a number smaller than 2? If we do, we can assume equal variance in the groups, which we should then tell R, because R by default doesn't assume that. So we should then tell R by setting the var equal argument to true. And with that we then get a standard t-test that's then also comparable to what SPSS and other statistical software packages give us. But we don't set that, I'm just going to jump back there. Then R is automatically introducing a correction, the so-called Welch correction, that allows us to work with data that doesn't have equal variance. It doesn't introduce a big difference into the results, so for t-tests you don't hugely need to worry about it. You just need to be aware that this is why you might be getting different results from what you expect in SPSS or so. So, what to remember? Firstly, if we see differences in our sample, then they can either appear between different conditions in the same group of participants, and that's then a repeated measures design, or a within participant design, just two are the same thing. Or they can appear between participants, and that's in a repeated samples design. Which tests we are running depends on the design. And for mean differences, if that's what we're interested in, differences in the average values between the groups, we would run t-tests with the t-test function in R if the variable under consideration is normally distributed or close enough to that. We'll practice that in class. Please do bring any questions that you have, and see you there.